We are going to examine the internal mechanics that allow a deep learning model to actually function. We'll demonstrate the specific architectural shifts that determine whether a network can interpret complex information or remain stuck in basic patterns. Over here on the left of our simulation is where the raw data enters the system. For our test, this is just a set of basic coordinates on a grid, labeled x1 and x2. These concepts provide the conceptual framework necessary for anyone looking to architect adaptable AI systems. We'll start with a simple data set. On our grid, the orange dots and the blue dots are separated by a distinct diagonal gap. We are feeding these coordinates into a basic single-layer perceptron. There are no hidden layers here. The raw inputs feed straight through to the output. This graph shows the result. When we run the model, it perfectly draws a straight line down the middle of the gap, accurately separating the two colors. This approach works in a sterile environment, but real-world data rarely organizes into neat, straight lines. If we ask this architecture to parse a complex shape, its performance drops immediately. Let's look at a more realistic distribution. Now our dataset forms a circle, with the blue dots completely surrounded by the orange dots. If we run our single-layer linear model again, it fails to separate the colors, because it cannot divide a circle using only a single straight line. Historically, engineers bypassed this by manually altering the math, a process called feature engineering. By squaring the x1 and x2 inputs and stretching the 2D grid into a 3D bowl, the outer dots are elevated away from the center. In this warped space, a flat plane can slide between the inner and outer dots. When viewed from above, that flat plane appears to the computer as a circular boundary. However, this requires a human operator to correctly guess that squaring the inputs is the exact formula needed to solve the geometry of the data. In multidimensional datasets, visualizing these shapes is impossible, which led the industry toward architectures that can deduce these patterns autonomously. To move away from manual math hacks, we can insert a hidden layer of processing neurons between the input and the output. For this test, we are keeping the mathematical activation setting for these neurons set to linear. When we run this multi-layer model against our circular data, it fails, behaving exactly like the single-layer version. This nested equation shows why. When you stack linear operations on top of each other, the entire structure collapses mathematically back into one basic linear operation. You could add dozens of layers, but if the math remains linear, the network still produces these rigid results. Architecture alone isn't enough. The model needs a mathematical trigger to handle complexity. That trigger is the non-linear activation function. We swap the linear setting for a function called sigmoid. Running the model now shows the hidden layers successfully bending to map the circular boundary around the data. We can increase efficiency further by swapping sigmoid for a modern alternative known as ReLU. This comparison shows that while both solve the problem, the ReLU function allows the network to converge much faster than sigmoid. Introducing non-linearity allows networks to adapt to arbitrary data shapes natively without human intervention. To prove this adaptability, we will load an entirely new data shape into the same network. We are using strictly raw inputs, with no manual feature engineering applied. The simulation shows the model instantly and autonomously mapping a boundary for this new dataset. This shows how the network derives its own features automatically, bypassing the limitations of the past. This implicit feature learning is the primary reason why modern deep learning architectures are so effective across different types of information. We've seen that single layers are physically limited to straight-line solutions. We observed how manual feature engineering is too rigid and labor-intensive to scale. We proved that adding hidden layers is ineffective if those layers are constrained by linear mathematics. And finally, we demonstrated that non-linear activations provide the flexibility for a network to map virtually any problem space. Understanding these interactions explains why deep learning is so adaptable, giving us a clearer perspective on how to structure networks for different types of data.